Good day and welcome back. So we'll continue with the discussion on past year, which is ulangan paper on STPM Physics 2019. Let's begin. So we have the first question, electric field on the surface of a positively charged conductor. So general formula of the electric field strength is equal to Q over 4 pi epsilon R. So we have a positive charge and it is on the surface where the R is the distance, which is 0 in this case. So electric field won't be 0 and it is not parallel. It should be perpendicular and it is outwards of the surface, which is answered as D. Next, question 2. So we have two hollow metal sphere of radii 5 and 7 centimeter, which carry charges of positive 6 and negative 4 microcoulomb. So we have a similar questions in 2019 that we will have electric field between the two surfaces, which is from the positive charge to the negative charge. So for this question, we are going to identify the electric field strength at P. So how we are going to get the electric field strength is by applying the Gauss law. So from Gauss law, we learned that electric flux is equal to the total charge enclosed divided by the permittivity of the medium. So we also have the electric flux is equal to EA. So we need to have a Gaussian surface, which should be a sphere in this case. So surface area of the sphere is equal to 4 pi r squared. So we're going to apply the formula to get the electric field strength at P. So the charge enclosed by the surface is only the 6 microcoulomb and does not include the negative 4 microcoulomb. So charge is only 6 microcoulomb divided by the permittivity divided by the surface area, which is 4 pi r squared, and r is 6 centimeter or 0.06 meters squared. And the answer would be 1.5 multiplied 10 power 7 watt per meter. Next, question 3. Capacitor consists of two parallel plates in which the distance between the plate can be adjusted. Capacitor is charged by connecting a capacitor to the battery, which is then removed. So potential difference can be increased by, so what we're going to see is that capacitor is charged and then isolated. So the charge on the capacitor is conserved. So to increase the potential difference, what we can do is to reduce the capacitance. So we have the formula of capacitance here. So what we are going to do is to increase the distance between the plates since it is adjustable. So the answer is C. So take note on the answer A. Touching the two plates only discharge the charge since the positive and the negative are now connected. So we're going to move on to the next question. Question number 4. Capacitor of 20 microfarad is discharged through a resistor of resistance 4 mega ohm. So we learn about discharge and we learn about the time constant, which is given as tau equal to RC. So here 20 micro multiply 4 mega, which is equal to 80 seconds. So this would be the first information we can get from this question. After 25 seconds, the charge on the capacitor is 2.9 microcoulomb. What is the time when the charge is 1.9 microcoulomb? So we learn about the charge response, which is during the discharging process is Q equal to Q naught multiply e to the power of negative t over the time constant. So we can find out the initial charge, or we can just apply the ratio to obtain the time elapsed. So here we're going to do the ratio. So we have 2.9 over 1.9 microcoulomb equal to e to the power of negative 25 seconds over 80. And then it is e to the power of negative t power of divided by 80. So this would be the equation we can build from the ratio. So now what we're going to do is to solve the equations. We have the e to the power of negative 25 over 80, which is equal to 0.73. So we're going to do multiply 1.9 divided by 2.9. We have the e to the power of negative t over 80 equal to 0.479. So we're going to apply the ln function. And then we have the negative T over AT equal to negative 0.735. So multiply negative 80 and you will get the final answer as 58.8, which is 59 second A. Moving on to the next question, question 5. We have two wires made of different materials have the same uniform current density. If both wires carry an equal amount of current, the wire can be deduced to have. So what should be the equal? So we have the same current density, we have the same current. So this is the formula of the current density, which is equal to I over A equal to NVE. So these two variables are equal, constant variable. So the area should be also constant, which is answer as B. So next question, question 6. A uniform silicon wire of length 0.25 meter is connected to a battery of potential difference 5 watt. Electron density, electrical resistivity are given. And what is the drift velocity of the charge carrier? So we learned about drift velocity and we have the formula of I equal to NEV. We don't have the current, but we have the voltage, resistivity, and the length. So probably we need to derive from the V equal to IR, and then we're going to get how we can get about the value of the resistance. So we have I is V over R equal to NAVE. And for the resistance, we have the resistance is equal to resistivity multiplied the length over the area. So we have the area, so we can get the expression of RA is equal to rho L. So we're going to further derive. So what we have is that the drift velocity V is equal to the potential difference divided by R and E, R and AE, where RA is equal to PL. So we have voltage, we have resistivity, length, electron density, everything. So now we can calculate the drift velocity, 5 watt divided by the resistivity, which is 2.303, divided by the length, 0.25 meter, divided by the electron density, 1.45 times 10 to the power of 16. And then divide by the electron charge. So we have the answer as 3.7 meter per second. So this is how we do derivations to solve this question. If not, you cannot solve it with the default formula you have in the textbook. Move on to question 7. So identical resistors or R are connected to an EMF of 10 watt, which circuit has a potential difference V out of 2 watt. So it is quite simple. We can apply the formula of potential divider to quickly obtain the voltage, or we also can learn about the voltage is proportional to the resistance. So we can apply the ratio. For example, the parallel of 2R of identical resistance is equal to 0.5 R. So from the ratio perspective, we have the resistance is 2 to 1. So the voltage is 6.67 to 3.33. So if you don't understand, you can calculate it by yourself, but this is through the knowledge of the ratio. So A and B has the same circuit structure. So V out here is 3.33 watt. And as for C and D, so we can see this is 0.5 R, okay, the equivalent resistance. And then we can get the ratio of the resistance as 2 to 1 to 2. So the voltage would be 4 to 2 to 4 watt. So now we can see that V out here is 4 watt and the voltage here is equal to 2 watt, and the answer is D. So we're going to question number 8. So this is quite interesting. Current of 2 milliampere flows from Q to P as shown in the diagram below. So if P is Earth, so what is meant by Earth is that it is can be also known as neutral. Okay, the voltage, okay, electric potential at P is equal to 0. So that is meant by Earth. Okay, what is electric potential at Q? Okay, so we are going to find out how to do this. So we have discussed similar things in question question in STPM 2019, there we're going to apply the Kirchhoff flow by drawing a loop. So we treat this as open circuit, and we can apply a loop, and we can build a Kirchhoff voltage law as what we have discussed before this. So actually there's also another way which I will show you later on. So let's apply the Kirchhoff voltage law. So we treat this as the voltage between point Q and P, which is VQP. And it is, according to the conventional current flow, so we have the negative plus 10 minus 6 volt. Okay, since the loop is flowing out from the positive terminal of 10 volt and it's flowing out from the negative terminal of 6 volt, so it is negative, and equal to the current 2 milliampere multiply the total resistance 5 plus 6 kilo ohm. So milli and kilo will be cancelled out. So solving the question, we have 11 times 2, 22, plus 6, minus 10. So we have the potential difference of Q and P is 18 watt. And since Vp is equal to 0, so VQP is also VQ, which is minus 0 equal to 18. So VQ is 18 watt. So another way to look at it is you can look at the polarity. So remember, current is flowing from the higher potential to the lower potential. So we know that electric potential at Q should be higher since the current is flowing from point Q to P. So here is positive and the P should be negative. So now we're going to observe the polarity at each of the components. For example, the battery is quite straightforward. It is plus, minus, and for 6 volt here is minus and plus. For the resistors, we follow the current as current is flowing from the higher potential to the lower potential. So here is higher and here is lower. Here is higher, here is lower. So now we can check the polarity and we can identify that which of the polarity follow the Q and P, and which of the polarity is against, which will be denoted as negative. So from here we can see that VQP is going to equal to minus 10 since it is against the polarity, plus 6 multiply 2 milliampere, plus 6 watt since follows the direction, plus 5 kilo multiply 2 milliampere. So actually you get the same answer as the on the left. So which is also, you can check it is similar. So what we have is the potential difference between Q and P is 18 watt. And since electric potential at P is 0, so VQP is VQ minus VP. So this is the definition of potential difference, which is the difference between the electric potential at Q and P. And there is 18 watt for Q, which is A. So if you need more information about this kind of questions, actually I prepared a list of questions which might be discussed in future. Let me know if you want to know about it. So continue with question number 9. Region of uniform magnetic field in negative Z is shown in the diagram. So electron enter the magnetic field in the positive Y direction. What is the direction of magnetic force? So it's quite straightforward. You just apply Fleming left-hand rule, and you need to be careful with electron that you need to reverse the direction of the force. So use your left hand and you should get the direction as left, but you need to reverse, which is to the right. Okay, so this is what happens when you deal with electron cases or the negative charge cases. So direction is positive X according to the graph. So moving on to question 10. So a long thin straight wire carries a current which produces the magnetic flux density of 10 microtesla at the point 2 centimeter from the wire. If the current is double, what is the magnitude of the magnetic flux density at 0.4 centimeter from the wire? So we can see there are two variables that is changed. First is the current is double, and you can notice the distance is also double. So according to the formula of magnetic flux density equal to mu naught I over 2 pi r, let us deduce or derive the magnetic flux that is in the new situations. So the new magnetic flux density is equal to mu multiply the double current 2I divided by 2 pi and double the distance 2r. And you can see it is actually can be cancelled and it is the same as the previous magnetic flux density. So the answer for this question is 10 microtesla. Answer is B. Straightforward. So let's move to question 11. So this question has been discussed before in one of my video. So you can check back on it and I will provide a link in the description below. So actually I provide also additional question for this question is to find out the force on each of these 3 wires. So you can check back on it and learn how to derive the resultant force per unit length on the wire. So we're going to skip this one and move to question 12. A coil placed in a horizontal uniform magnetic field of flux density 25 millitesla with its plane at an angle 30 degrees to the vertical as shown in the diagram below. So this is quite dangerous if you don't really observe the angle carefully. So what we are going to do is we have the radius 10 centimeter, number of turns 25, and what is the magnetic flux through the coil. So we learned about NBA cos theta, but you need to be careful that the angle is referred when it is between the normal component of the coil to the magnetic field. So we need to be very careful and observe about it. So this is our coil and the normal component is in this direction. So what we need to is the normal angle that we have is the magnetic field between the magnetic field and the normal component. Okay, but the angle here, so we need to check. So it is equal to the same as 30 degrees. So for this question, we actually use NBA cos theta. So if you refer back to the previous past year, it is actually NBA sin theta. So you can compare these two questions to find out the difference and make sure you will be careful if there is similar question in the future. So we're going to find out the magnetic flux linkage. We have the number of turns 25, multiply the magnetic flux density 25 millitesla, multiply the area, which is area of circle pi r square. Radius is 10 or 0.1 square and cos 30 degree. And you would have 0.017. So there's an error in this question, but it is equal to 1.7 multiplied 10 to the power negative 2 Weber. So I'm sure there's a typo here. Moving to question 13. So when the current flow through an inductor of inductance 0.75 Henry, energy stored in the inductor is 3.5 joule. So what is the current? So straightforward, we have energy equal to half Li squared. So energy is 3.35 joule multiply 2 divided by the inductance 0.75, and you have the value of I squared is this. And what you're going to do is to square root the answer, and you would get the current as 3 ampere. Moving on. So question 14, resistor of resistance 200 ohm is connected to a sinusoidal alternating current, peak voltage 340 watt. So which statement is true about the circuit? So root mean square voltage is 170 watt. Let us check. So 340 to get root mean square is 2 divide, so 2. So 240, which is wrong. So root mean square of current, let's check. So we have resistance or voltage divided by R, 200. So 1.2 ampere, which is also wrong. For the peak power, we're going to use the power of P equal to VI. So the peak voltage 340 multiply the current. Or maybe we can use V squared over R divided by 200. So 578 watt. As for the average power, so remember power is equal to VI. So if we are using average power is root mean square voltage multiply root mean square of current, which is half of the peak power. And half of 578 should be not 509, but it is 289 watt. So this is how you calculate the average power. So final answer is C. So last question for today. So we have a resistor connected in series to an inductor and an alternating current supply of constant peak voltage but of frequency that can be varied. So a resistor with an inductor that is RL circuit. So which graph show the variation of the peak current with the frequency? So we learned about current is the ratio of the applied voltage to the impedance, and the impedance is equal to the square of R square plus the reactance of the inductor, which is omega L square. So as the frequency increase, so what we can expect is current is decreasing as I is proportional to inversely proportional to 1 over inversely proportional to omega. So the expected answer is D. Okay, so probably someone might be curious with B, but the normal conventional graph for the reciprocal is C. Is D. So it is safe to choose answer D for this question. So that's all for the section A for Ulangan paper 2019. So thank you for watching. Hope to see you again in future.